Okay, so respected session chairs, conference committee members, volunteers, and other participants, a very warm good afternoon to everyone. I'm Devika S. Kumar from the Indian Institute of Technology, Kharagpur. I'm the second author of the paper titled An Efficient Linearizing Demodulator Interface for LVDT. And I'm here on behalf of myself and the other authors to present the aforementioned paper in this esteemed conference. As we know, in today's world, sensors play a very vital role as they provide a link between the environment and the systems, devices, etc. that we use, be it data acquisition, control, IoT, etc. Be it anything, sensors are there. And we can see that many of the sensors that we use, that are in use, are non-linear in nature. That is, after a particular range, the output is not proportional to the input. One of the main objectives of this proposed scheme is basically to provide a linear range extension to a certain set of sensors. So the sensor that we have considered for our study is a linear variable differential transformer. It is a inductive displacement sensor which produces an output voltage which is directly proportional to the displacement of its ferromagnetic core. So basic principle is that when there is a displacement in the ferromagnetic core, the mutual inductance of the secondary coils with respect to the primary coils changes linearly, as a result of which there is a voltage generated in the secondary coils, which are different in nature. And as a result, there would be a voltage difference, which is V naught, and that is basically the output of the LVDT. And in conventional LVDTs, we use AC excitation. And as a result of which, almost all LVDTs, we need a demodulator system to actually get an proper output from it. LVDT has various applications in aerospace, flow control, measurement, and automotive vehicles, etc. And as we can see here, this is the typical transfer characteristics of an LVDT after a certain, here, B to A will be if it is the given range, and this particular range depends upon the manufacturing of LVDTs. It can differ from one LVDT to the other, and our object is to provide a linear extension. If it is B to A, make it B dash to A dash. That is one of the major objectives. Now coming to the literature map, there have been many proposed ideas for linear range extension, but what here the thing is, it uses a large number of components, complex components like precise sinusoidal oscillators and phase matching circuitry and maybe matched reference voltages as well. So, and here there is another scheme that was that was proposed by the same authors. I was not included though in IEEE AppsCon 2024. So this work can be seen as an extension of what was done there. And one of the major points that has to be noted in the previously proposed scheme is that all of it uses a demodulated output from the LVDT. So basically, we need external demodulator circuitry for before using these proposed schemes. So here, that is where our scheme comes into the picture, which is a demodulator interface, which is capable of linearizing the sensor output. So coming to the proposed scheme, so here the major inputs are the reference voltage VR and the control signal Vcon, which is a square wave basically, a square waveform basically. So here, this is the demodulator circuitry, and here this part consists of the linearizer circuit, which will be explained further on. Here we have an integrator along with a switch in parallel with a capacitor, which is acting as a sawtooth waveform voltage generator. And then we have a V2I converter, which converts the sawtooth voltage waveform into a current waveform, which is then fed into the primary coils of the LVDT. Now, as a result of this current, there is a DC voltage which is generated across the secondary terminals, but it will be having certain spikes because of the switching that is done. And then we have a switch SW2. Now, what this switch SW2 does is to remove the effect of this transients or the switching that is causing those spikes in the waveform. Then we have the linearizer circuit, which I'm gonna further explain. Before that, we have here, when the switch SW1 is opened, basically this voltage over here, VP1, will be ramping down. And during that instant, SW2 will be in position 1. And when SW1 is closed, that is VP1 will be almost 0. That is when the switch SW2 will be connected to 0. Okay, and so if VLVDT is the output from that switch SW2, we can say that the LVDT is having a cubic transfer characteristics. Normally, what we expect is a linear relation between displacement and voltage. However, in order to for this linear range extension, we are considering the model where the transfer characteristics is cubic in nature. So this is the linearizer part. Here, what the linearizer circuit does is basically it represents this VLVDT as a cubic function of the linearizer output. So as we can see over here, on comparing equations 5, 5 and 8, the VLin will be directly, the linearizer output will be directly proportional to Y, provided these particular conditions are met for the resistors R1, R2, R3, and R4 in the linearizer circuit. Now, further, the linearizer output is sent through a low-pass filter, which is having, which should be having a cutoff frequency, which is much less than the frequency of the control signal that we are using. Also, the low-pass filter will be cancelling out the noise due to external devices as well as electronic devices that are used. Here, coming to the simulation studies, we have used LTSpice software for the same, and here are the results. Here we can see that VP1, the sawtooth waveform, is produced at this particular node, and after the V2I converter, we have the primary current IP, and then, as I said, this is the DC voltage that is produced. But here, as we can see, we have spikes over here. And this can be this can affect the system. The spikes are definitely not desirable, right? So the spikes in the DC voltage is further translated to the output of the instrumentation amplifier as well. But here, as we can see, by using that switch SW2, we are basically removing these spikes from the instrumentation amplifier output. So that is the use of that SW2. And then here we have the linearized output as well as the LPF output. Now from the simulation studies, the nonlinearity values are computed for different spans, which is 50 millimeter and 100 millimeter. And simulation studies show that 0.31%, there is for a span of 50 millimeter, there is a nonlinearity of 0.31%, and for a span of 100 millimeter, it's 0.74. Now, coming to the experimental setup, here is the LVDT that we have used, and here is the interface that we are talking about. And all measurements have been done using standard measuring instruments. So here, the experimental data has been plotted over here, and it can be seen that for a span of 100 millimeter, the nonlinearity is just 0.9%, where in a typical LVDT, the nonlinearity for a span range of 100 millimeters is 5.98%, which is like about a 6 to 7-fold reduce in the nonlinearity value. That can be seen over here. Here, a table is mentioned comparing the values of a conventional LVDT with simulation and the experimental results. We have also conducted repeatability tests for 400 samples per reading, and the standard deviation, signal to noise ratio, repeatability error, etc. are considered. Here is the waveforms that have been generated by the experimental setup, and the error analysis for the same was also conducted, and it could be observed that it is the tolerance values of the resistors used in the linearizer circuit that contributes to the error most. So even for a 0.1% of tolerance, it could be seen that an error of 0.18% was seen in the could be seen in the output, and hence precision decade box resistors were used to implementing this experimental setup. And here is a comparison between our scheme and other existing schemes. Here, as I said before, we are providing a linearizing as well as a demodulating interface, while other setups do need external demodulators. And as I mentioned, the nonlinearity values as well are shows that how efficient our system or our scheme is. So to conclude with, as I've said, we are proposing a demodulator interface which is capable of linearizing sensor output. And here, the sensors that we are talking about is not just LVDT, any inductive sensor, any inductive sensor which is like having any inductive sensor which mostly requires demodulators can come under the scope of this. And as I said, fewer components are used over here in comparison to other proposed schemes, as well as the complex components are avoided. And as for future plans, we have miniaturization and converting this proposed scheme into an integrate it into a chip. And we also plan to link linearization with digitization of the LVDT output as well. So here are the references that has been used. So that was it for my part. Thank you. Any questions?